Good morning, everyone. Hope you had a good weekend. We're going to get started now. So the recording has begun. We're into chapter 4 again. So we bounce back and forth between chapter 13 and chapter 14. Chapter 13 was on space curves. So we introduced those. So those are vector valued functions. And then we looked at derivatives. And then we moved over to chapter 14, looked at multivariable functions and their derivatives or their partial derivatives. And then we bounced back to chapter 13 in order to see what derivatives can do for us with space curves. So that was 13.3, arc length and curvature, and 13.4, motions in space. And now we're jumping back to chapter 14 and seeing what derivatives can do for us there, what the partial derivatives can do for us there. And so that's kicking that off with the chain rule. And so that's today's topic, is the chain rule. It's the same as it was in Calculus 1, functions of a single variable, in the sense that what the chain rule does is it addresses the issue of, if I've got a composition of functions, how can I work out the derivative of the composition in terms of the derivatives of the individual pieces that make up that composition. And so there's the chain rule stated down at the bottom there, but we'll get to that in a second. What I want to do is I want to come back to a problem that we've seen before. This is a problem from Calculus 1, and it's a related rates problem. And I just want to go through it as we would, a related rates problem as we normally would. And then we'll pick off some of the patterns that happened in there. Some patterns that we may or may not have observed when we were in Calculus 1, but now that we have a few more tools in our toolbox, we can see that there are some things that came up in our solution that we can utilize and exploit, and that are true in general. So here's the idea. We've got some sand that's being poured. I can imagine it off of a conveyor belt onto the top of a pile. And as the sand falls onto this pile, it forms a cone. And both the height and the base radius of the cone will change over time. Over time, more sand gets piled on. So we've got our base radius and our height that are going to be changing over time. And we're interested in, at a particular moment in time, when the sand pile has a height of 5 and a radius of 2. We know a little bit about its rates of change of those two variables at that point. At what rate is the volume changing? So we're interested in knowing how the volume changes at a particular time. So what we're going to do is just run like we would any related rates problem. We're going to say we're interested in the rate of change of volume. So let's relate the volume to the two variables we know. And so this would be 1/3 pi r squared h is our volume. So that is just our volume of a cone formula. If you're wondering where I pulled that out of, so that's one of the things we probably did derive when we did volumes of solids of revolution, but this is just a formula of a cone. And I like to just think of it as it's 1/3 of the volume of the corresponding cylinder that you would get with base radius r, circular cylinder, base radius r, height h. This is the volume of the cone is just 1/3 of that. So what do we have here? Well, where r and h are functions of another variable t, which we'll use to denote time. So the idea is we've got volume. It's expressed in terms of the base radius r and the height h, but both of those are functions of another variable t. So this is our typical setup with a related rates problem. The very next thing we do is we go ahead and differentiate. So we differentiate with respect to the variable t. So we go dv dt, because I'm thinking of volume as a function of time. So it's just a function of a single variable. So these are our regular derivatives. dv dt is equal to, and now I want to differentiate the other side, and that's just a product. It's a product of two functions. It's a product of the r squared function and with the h function. both of those are functions of t. So when I differentiate r squared with respect to t, I'm going to use the chain rule because it's a squaring function and an inside function of r, which is a function of t. And then the other half of that product is the h function. I'm going to have to differentiate it with respect to t. So when we do the derivative with respect to t, just like we did in calculus 1, this is our related rates problem. We differentiate, let's say, the first function, the r squared first. So that would be a 2/3 pi r h. And then we differentiate, sorry, the r function, the inside of the square is dr dt. And then we add to that the derivative of the other piece. So that's 1/3 pi r squared is the first function, and then we multiply by the derivative of the second function, dh dt. So I'll indicate that here, that this is product rule. So I'll write a PR. So that's the product rule. Now that we have a relationship between the rates of change of our input, or our variables r and h, sorry, and our variable of rate of change of our variable volume, we can now plug information in. So now we look at, for the particular moment in time when h is 5, r is 2, we know that dh dt, so h is increasing at a rate of 0.4, that means dh dt is positive 0.4. dr dt, radius is changing at a rate of 0.7, so dr dt is positive 0.7. So with this information, we have that dv dt is equal to 2/3 pi times 2 times h times dr dt, which is 0.7, plus 1/3 pi r squared, so that's 2 squared, times dh dt, which is 0.4. And that's cubic. So we look at the units. It's volume, so that's cubic meters per, and time is minutes. So that's cubic meters per minute. And you could simplify this expression a little bit for the answer. If you're interested in a calculator approximation, you can throw it in your calculator, whatever you can do with the last value here. But we've got the answer here essentially in unsimplified form. So there's our brief summary of how we approach the related rates problem in calculus 1. Why am I even doing it here? This is the reason. So this derivative that we just computed. So what we were doing is we were thinking volume is a function of r and h, but r and h are both functions of time. So volume is a function of time. So we just went through and differentiated using the product rule and then the chain rule from calculus 1 every time we encountered some expression involving either r or h. We were thinking of, r is the outer, maybe there's an even outer function. So there's the squaring function was the outer function, and then r is another outer function because ultimately it's a function of the variable t. So if I look back at this derivative line, what I see is that there was some expression in front of the dr dt and another expression in front of the dh dt. And those we got while we were doing derivatives, effectively doing that product rule. But now that we've got multivariable calculus and partial derivatives under our belt, can we recognize that as something related to the original volume? Do we recognize that as a partial derivative? And the answer is, yeah, that's the partial derivative of v with respect to r. And this one here is the partial derivative of v with respect to h. So when I look at this formula, which I computed entirely using calculus 1 techniques, product rule, and then one-dimensional chain rule, what we see is that that formula can really be expressed as, I wanted to differentiate volume with respect to time, first differentiate it with respect to radius, and then differentiate the radius with respect to time. And then add to that the derivative of the volume with respect to the height, and then multiply by the derivative of the height with respect to time. And it turns out that that's not something that's just true in this case, it's actually true in general, and that's known as the multidimensional chain rule, or we just call it the chain rule for short in this class because we're dealing with multidimensional objects. So that's what we've got down at the bottom. Suppose that we've got a function of two variables, and this can extend to more variables. Once we see how to extend to two, like many things in this course, we just continue on doing the natural extension to higher variables, higher number of variables or higher dimensions. So if z is a function of x and y, then f has continuous first order partials, but we're thinking of x as ultimately a function of t and g as a function of t. So that's these lines here. X is really a function of some third variable, or I guess a fourth variable in this case, x, y, z, and now a fourth variable t. Y is also a function of that fourth variable t, and we're assuming they're differentiable functions. Then z is a differentiable function of t. That's a one-dimensional calculus problem. This is z is a function of t, so it's differentiable, so therefore we can find its derivative. So z is a function of t, we're now back into calculus 1. Z is a function of one variable, namely t. So how do we compute its derivative? And that's what the chain rule tells us. Chain rule says in order to compute its derivative, that's dz dt, we first take the partial derivative of z with respect to x, and then multiply by the derivative of z or x with respect to t. And then add to that the partial with respect to y times dy dt. I want you to pay very particular or very close attention or particular attention to when I use d versus when I use del. The d is an indicator of a function of a single variable. So that left-hand side, dz dt, that's because we're thinking of z as a function of a single variable t. But the very first expression on the right of the equality is and I'll call it del z, del x. Normally I've been interchanging those names, del and d's, but the really script or fancy d, the partial derivative d, we're using del z, del x there because now I'm thinking of z as a function of two variables and I want the x partial there. And then I multiply by dx dt because x is a function of a single variable. So there's only one derivative associated with it, the derivative with respect to t. And then I add to that the partial derivative times the derivative of y with respect to t. So that's our chain rule. And it was, in some sense, it was motivated by this stuff above on related rates problems. But the chain rule is our technique for dealing with derivatives of compositions in multiple dimensions. So let's look at an example. We're going to find dz dt if we've got z is arctan of x and y, but x and y themselves are both functions of t. What is the derivative of z with respect to t? So I'm going to say maybe the substitution and differentiate method. We'll do that first because this is sort of the obvious, maybe the obvious way to deal with this. Pretend you didn't know anything about partial derivatives. Pretend you're sitting in calculus 1 and you're asked to find dz dt. And this is the question you were asked to do it for, find dz dt for this. Well, this would be the technique you would probably use. You'd say, oh, well, z, that's a function of x and y. Oh, but x is t squared and y is t cubed. So this is arctan of t to the fourth plus t to the sixth. Okay, so now I've expressed my function entirely in terms of t. Now I don't even need to worry about the x's and y's because they're gone. And so now I can differentiate. dz dt is equal to derivative of arctan is 1 over 1 plus the inside squared. And then we multiply by the derivative of the inside. That's our chain rule in calculus 1. So that's 4t cubed plus 6t to the fifth. And there we go. We've done our derivative. So that would be our just substitute, put everything in terms of t, and then do the derivative approach. But we're trying to establish another technique for doing this. That's the multidimensional chain rule. So let's see that if we do the multidimensional chain rule, we get the same result. And so what the multidimensional chain rule says is, don't bother substituting right away. Just keep your outside function. That's the arctan of x squared plus y squared. Just keep that and do its derivatives. And then also keep your inside functions, your x equals t squared and your y equals t cubed. Keep those separate. Do their derivatives. Once you've done those derivatives, then you piece them together using the chain rule. And so this is telling us that in order to get dz dt, I would first take the partial derivative of z with respect to x, and then multiply by dx dt. And then add to that the partial derivative of z with respect to y, and then multiply by dy dt. So that's the chain rule. And we'll indicate that here because this is our new approach. That's our, and I keep referring to it as a multidimensional chain rule, but we'll just abbreviate that as chain rule because we are in calculus 3, and that's what the chain rule means to us. So what is the partial derivative of z with respect to x? Well, that would be 1 over, it's arctan, so it's 1 over 1 plus the inside, all squared, times the derivative of the inside function. This is a partial with respect to x, so we're differentiating the inside with respect to x, so that becomes 2x. So that's our partial derivative, and then we multiply by dx dt, so that's 2t. And then we add to that the partial derivative of z with respect to y, so that's almost the same as the partial with respect to x due to symmetry, except there's a 2y up top. And then we multiply by the derivative of y with respect to t. So that's 3t squared. And at this point, we've kind of got things mixed in the sense that our partials are in x's and y's, but our derivatives of x's and y's with respect to t are in terms of t. So let's just put everything in terms of t, the final variable that z is a function of. So that would be 2t. Actually, that's going to be, I'll multiply these together. So it's 2x times 2t. So that's 4xt, but x is t squared. So this is 4t cubed. And we'll put it over that common denominator of a 1 plus t to the 4th plus a t to the 6th all squared. And then I'm just going to put the numerator, the other part of the numerator in from that second term. That's a 2y, 3t squared. So that's going to be a 6yt squared, but y is t cubed, so that's a 6y t to the 5th. And there's our final result. And notice they are the same. So we got the same result. One, we did a substitution and then a differentiation. The other one, we did a chain rule and then the substitution. So the chain, we did the derivative first and then substituted second. And to do the derivative first without substituting, we do the chain rule. Differentiate through with respect to its intermediate variables, and then substitute in terms of the final variables at the end. So you may say, the chain rule took a lot longer in this case. And absolutely, it did in this case. But in general, the chain rule is going to be quite a handy tool for us. And we're going to see that it's worth knowing, not because it makes things longer to do and just keeps it separate, but because in some instances, it's going to be the only real way we can actually solve a problem. Shouldn't it be t next to the 6? Oh, it should be. Thank you. Yes, it should. That y there, I don't know why I wrote y. It should have been a t. Thank you. Too many variables to juggle around, I guess. Yeah, so that was a 6t to the 5th. Thanks for pointing that out. All right, let's have a look at the next one. So this next one is virtually the same problem as the previous one, except now there's 3 intermediate variables. Each one of them are functions of t. And so we'll go ahead and we'll do the chain rule approach. I mean, we could do the substitution approach as we did above, and I'll leave you to verify after we do it using the chain rule. You can check to see that you get the same answer using the substitution approach first, put it in terms of t, and then just take its 1d derivative. So what is dz dt? So that is going to be, oh, it's not z in this case because z's an intermediate variable. W is the variable that we are looking at as our outside variable there. So we're interested in what is dw dt. And so this, I guess I should correct this then. Find, I shouldn't really say dz dt, find the derivative, just because in the first case, z is our variable of choice, but in the second case, w is our outermost variable. So we want to find dw dt. So this is going to be the derivative of w, partial derivative with respect to x, times dx dt, plus dw dy, dy dt, plus dw dz, dz dt. So there's our chain rule. As I said, once you know how to do it for two variables, you can do it for more by just continuing the pattern along. We just add to the original expression, we just add the next partial derivative. So the partial derivative of w with respect to whatever the next variable is as the intermediate variable times the derivative of that variable with respect to t. And then in this case, we get the partial derivative of w with respect to x. That's going to be 2x over 1 plus the inside all squared. That's the derivative of the arctan part, x squared plus y squared plus z squared, times dx dt. So that's times 2t, plus 2y, 1 plus x squared plus y squared plus z squared squared, times dy dt. That's 3t squared, plus 2z over 1 plus x squared plus y squared plus z squared squared, times dz dt, which is 4t cubed. And then we can put all that in terms of t. So they're all going to have the same denominator, 1 plus t to the 4th plus t to the 6th plus t to the 8th, all squared. And then our numerator becomes 4 times xt, so that's 4t cubed, plus 6 times yt squared. Y is t cubed, so that'll be 6t to the 5th. And then the last one is 8 zt cubed, or 8t to the 7th. And there's our final result. And you can probably eyeball it now when you just, if you did the substitution first, even in your head, you might be able to do the substitution and then do the derivative, and you'll see that you get the same result. Okay, so those are a couple of examples using the chain rule, or this form of the chain rule that says you've got an outer function, which is a function of many variables, but each of those variables, intermediate variables as we call them, each of those intermediate variables is a function of a variable t. So we can do partial differentiation of the outermost function in terms of each of the intermediate variables, and then multiply by the derivatives of those intermediate variables in terms of t. Now, what happens in the case where your intermediate variables are not just functions of a single variable t, but they are functions of more variables? So in this case, we've got the chain rule where we've got several independent variables. So we're thinking w is a function of x, y, and z, but x is a function of u and v, y is a function of u and v, and z is a function of u and v. So w ultimately, in the end, is a function of u and v. So that means we can ask for its partial derivatives. What is the partial derivative of w with respect to u? What's the partial derivative of w with respect to v? Rather than doing the substitution first, like we did in the first example, where we put everything in terms of t and just took a derivative, rather than doing that in this case, just putting everything in terms of u and v and just running through our regular partial derivatives, we can instead keep these things separate. The outermost function in terms of x, y, and z, and then the inner functions, the x, y, and z, in terms of their variables, u and v, we can keep them separate, do their derivatives, and piece them together. And that's what the chain rule is telling us here. It's saying if I want to compute the partial derivative of w with respect to u. I compute the partial of w, and I'll just do an indicator here. We do it w with respect to x. So we do the partial derivative with respect to that first variable, and then the partial derivative of that intermediate variable with respect to u. And then we just go across. We say, okay, now we do the partial with respect to y. And then the partial of y with respect to u. And then we go to the next variable, the partial with respect to z. And then the partial of z with respect to u. So we just work our way across. Want to know dw du, go dw dx, dx du, plus dw dy, dy du, plus dw dz, dz du. And similarly for the v's. The only difference there is if v is my variable of integration, then that's the only update. The only update is those things I underlined. Is in the first line they're u's, in the second line they're v's. I'll underline the first one as well. So let's go ahead and do an example. We've got w is arctan of x over y. X is a function of u and v. Y is a function of u and v. So we can compute the derivatives of w with respect to partial derivative of w with respect to u and the partial with respect to v. So that's a good question. So in the chat, there was a question about this kind of idea of a complete derivative. And it was, could you sum the two to get a complete derivative? In some sense, so there is this notion of a total derivative. And the total derivative, it's not necessarily going to be the sum. What we're going to do is we're going to look at what essentially is a derivative in a certain direction. Because a derivative in some sense is just trying to capture the rate of change. Derivatives are always with respect to a single variable. So the derivative with respect to u or the derivative with respect to v, that says if you change u a little bit, how is w changing? Or if you change v a little bit, how is w changing? So a derivative is always if you change this one variable, how does the output change? What's the rate of change in the output? And because in multiple variables, we've got many different directions, we won't consider in some sense a complete derivative, but we will consider directional derivatives. So what is the derivative in a certain direction? And there it would be the dot product of the direction with the vector made up of these partials. So yeah, so Doina, you're onto something there. And that's what we'll get to later on in this chapter. So good question. All right, let's have a look at the example. So we're interested in dw du. So that would be first dw dx, dx du, plus dw dy, dy du. And again, particular attention to the notation. I'm using the fancy D or the script D or the del notation for all of these derivatives because they're all partial derivatives now. Everything's a partial derivative. There's no function of one single variable. Everything's functions of multiple variables. So what is dw dx? So that would be 1 over 1 plus the inside function squared. So that's the derivative of the arctan part. And then we've got to multiply by the derivative of the inside, the x over y with respect to x. So that would be a 1 over y. So that's the derivative of the inside of the arctan function, the x over y derivative with respect to x. So that's taking care of the dw dx. Then we need to multiply by dx du. And so that will be times 2u. And then we can go to the next partial, dw dy. So the derivative of the arctan is 1 over the 1 plus the inside function squared. And then we need to multiply it by the derivative of the inside function, x over y, the derivative of that with respect to y. So that would be, x is a constant because we're doing the partial derivative here with respect to y. So we think of x as a constant. So it's just x times the derivative of 1 over y, which is negative 1 over y squared. So that's our derivative of the inside with respect to y. Derivative of xy with respect to y is negative x over y squared. And then we multiply by the derivative of the inside function, or sorry, the derivative of y, which is the innermost thing, with respect to u. And so that becomes a 2u as well. And so now we can put everything in terms of u and v. This would be a 1 over u squared minus v squared all over 1 plus x over y. So that's u squared plus v squared all over u squared minus v squared all squared times 2u. So I'll put the times 2u up top.
Sorry, quick question.
Yep, go for it.
At the end of the previous sentence, derivative of y with respect to u, isn't it supposed to be 2v? Or is it
so-
the other way around?
So this one here, this part there.
Yeah, because what I'm noticing is dy over du equals dx over du, and
Yep, and
so
that's just
one of them is not right.
that's just because both of them have that u squared there. Right, the derivative of x with respect to u
Oh, right.
would be 2u. The derivative of y with respect to u would be 2u because they both are made up of u squared plus something involving v. Thanks for the question. And so then we've got a negative x, which is our u squared plus v squared, all over y squared, which is u squared minus v squared, times 2u all over 1 plus x over y. And I want to get the x over y's in terms of u's and v's, so there's a lot of stuff here. U squared plus v squared over u squared minus v squared all squared. So there it is expressed in terms of u and v, not simplified at all, but there's our partial derivative. So in the next one, I'm just going to leave it at the line before where we've got our partials involving both the x's and the y's and the u's and v's, because that's the chain rule. That's the main part of the chain rule. So let's see how to do the next partial. So we're interested in the partial of w with respect to v. So it's the same as it was before, partial with respect to the intermediate variable x, but now in this case, it's dx du, or sorry, dx dv in this case, because v is our variable of integration or differentiation, sorry. So I'll change those to green just to focus our attention there. Plus dw dy dy dv. So that's the only change, is that variable v as opposed to the variable u above. So that means our first partial derivative is the same, dw dx, times dx dv. So if I look back up here at x, it is u squared plus v squared. So its derivative, partial derivative with respect to v is 2v. And then I've got the next piece, partial w with respect to y, times the derivative of y with respect to v. So I look up at the expression for y. Y is u squared minus v squared. So its derivative with respect to v is minus 2v. And then we could put in terms of u and v. I'm not going to do that for this one. I did it above. It took a while, and it didn't really give us any new insight other than just to say that this thing is a function of u and v in the end, and here's what it looks like in its unsimplified form. But the idea is we've done the chain rule now, done the derivative. All right, let's have a look at another example. And with these examples, I just want you to get the feel for the chain rule. It's sort of a pattern that rolls off the tongue. It's dw dx, dx dv, dw dy, dy dv. And so you're just going to start reading off the intermediate variables and computing their derivatives with respect to the variable of differentiation that we're interested in. So in this case, we've got w as a function of u, v, x, and y. So it's a function of 4 variables, but u and v are functions of x and y. So these are functions of x and y. U and v our functions of x and y. And then there's x and there's y there as well. So in some sense, the idea was we took this function representing w, and we collected together some x's and y's that formed a pattern and called those u, and collected some other x's and y's together that seemed to form a pattern, called those v's, and left the extraneous x's and y's just sort of in there as well. However you want to think about it, we're trying to deal with a function that looks like this. And we'll see in the very next example where this would come up in practice. This is just more of a theoretical example to just get the pattern of the chain rule down. So we want to know what is dw dx. So dw dx, we just go through, the function is f. We've got its inner variables, which are the intermediate ones, which we're ultimately going to differentiate with respect to x's and y's. So here's our pattern. The derivative of w with respect to x is the derivative of the outside function f with respect to its first intermediate variable, u, times du dx. And then we add to that df dv, because that's the next variable, times dv dx, plus df dx times dx dx, plus df dy times dy dx. So we've just read across that expression for w. F is u in terms of u, v, x's, and y's. We just read across, and for each of those variables, we had a term in our chain rule. So again, indicate that this is the chain rule that's giving us this derivative. And now at this point, we can do a little bit of simplification. U and v are just some functions of x and y. X's and y's are therefore our independent variables in the end. They're what everything is a function of. And so when I see an expression like this, dx dx, what's the derivative of x with respect to x? What's that going to be equal to? So the derivative of x with respect to x, yeah, that's 1. So think of it as you've got a function of multiple variables, and you're differentiating it with respect to x, and it's just f of xy is x. The derivative is just 1. How about this one? Dy dx. Think of, you're differentiating a function involving x's and y's, and you came up across a term that was just y. What's its derivative with respect to x? So what's dy dx? That one's 0, exactly, you got it. Yeah, because when we differentiate y with respect to x, we treat y as a constant. It's an independent variable of x, so it's independent of it. And so its derivative would be 0. So that means that this becomes df du, du dx, plus df dv, dv dx, plus df dx. And that's it, because that's multiplied by 1, and then the other term disappears because it was multiplied by 0. We can do the same thing for the other partial, dw dy. So that's going to be df du, du dy, plus df dv, dv dy, plus df dx, dx dy, plus df dx, df dy, dy dy. Okay, sometimes when you get to the fourth term, you start to go on autopilot and then forget what it is you're actually doing. Again, dx dy, that's going to be 0. So the derivative of x with respect to y, that's 0. But the derivative of y with respect to y, that's 1. So the partial derivative of the y function is 1. So this becomes df du, du dy, plus df dv, dv dy, plus df dy. That's that one coming down there.
Hi, Professor.
Hi.
Could you explain one more time why dy dx and dx dy is 0?
Sure. Let's have a look at something we're used to seeing. Say I had a function f of xy, which is equal to x plus 2y, something like that. And I asked for what is the partial derivative of f with respect to x. What would the answer be? So this is back to 14.2. So if I want to compute the derivative of this with respect to x, I would just treat the y's as all constants and just do its regular derivative with respect to x. Exactly, it would be 1 plus 0. And the reason is the derivative of x with respect to x is 1, whereas the derivative of y with respect to x is 0, because I'm treating y as a constant. Does that make sense?
Yeah, that does. Thank you.
Okay, you're welcome. Right. So you may look at this example and just say, well, that was an awful lot of variables and in some sense an awful big mess. But the idea was the chain rule had a structure, it had a rhythm, a tempo, and we just sort of followed that rhythm as we went through it. Where would we use something like this? Well, that's our immediate next example, and that's known as implicit partial differentiation. So with this, I want you to just think, if you want to grab sort of something concrete, think sphere. X squared plus y squared plus z squared equal to 1. And I'm interested in finding the tangent plane to a sphere at a particular point. So if I want to find the tangent plane, I need to know what dz dx is, and I'd also need to know what dz dy is, because I need those two partial derivatives to start to construct the tangent plane. So if I'm thinking the sphere, we'd want to find dz dx, and dz dy. Now, one way to do that is to solve this equation for z, writing it as the square root of 1 minus x squared minus y squared. So we get z as a function of x and y. But then I'd have to know if I'm on the upper hemisphere or the lower hemisphere. And I take a positive root if I'm up top, a negative root if I'm down below. But, just like in calculus 1 with implicit differentiation for curves defined in that way, we can eliminate all that by just saying, I've got a function here in x, y, and z, and I'm interested in finding the partial derivative of z with respect to x. So this is how we're going to think of this situation. We're going to suppose we've got a function of 3 variables, x, y, and z, and we are interested in the surface, which is all x, y, z values for which that function is 0. So in our case of the sphere, that would just be bring the 1 over to the other side as a -1. And so we'd get x squared plus y squared plus z squared minus 1 is equal to 0. And so our function would be x squared plus y squared plus z squared minus 1. So I'll just write that in here. I'll put it in here as a -1 equal to 0. And so this is what we're thinking of our capital F of x, y, z function. And so what we can do is we can find the derivatives dz dx and dz dy by doing this technique known as implicit partial differentiation. And the results are written here. The derivative of z with respect to x is just the x partial of that function of 3 variables over the z partial derivative of that function of 3 variables with a negative sign in front. And similarly for the partial derivative with respect to y. Let's see why this is the case. It's just following from the chain rule, but we'll see why.
Professor?
Yep, go for it.
Before we continue, can you scroll up to the previous example we just did?
Yep.
So at the very end of the very last line, like where it says dx over dy. Oh, never mind. I miswrote it.
Oh, yeah. Okay, perfect.
Yeah. No, I thought it said dx. Yeah.
You got it. Perfect. All right. So then in this case, we've got this f x, y, z equal to 0. And so what we're going to do is we're going to go through and we're going to differentiate with respect to x. So I've got an equation. I'm going to differentiate with respect to x. And so it's a partial derivative. So what we get on the right-hand side is we get the derivative of f with respect to x times the derivative of x with respect to x plus the derivative of f with respect to y times the derivative of y with respect to x plus the derivative of f with respect to z times the derivative of z with respect to x. And that's got to equal the derivative of the right-hand side. If the two functions are equal, then their derivatives have to be equal. So I just differentiated the left-hand side using the chain rule. Derivative of the right-hand side, well, that's just the 0 function, so its derivative is 0. So I took the equation that described my surface, and I just differentiate through both sides of that equation with respect to x in this case. And then we go and we look at the expression and we say, well, dx dx, that's 1. So just like we've argued in the example above. Dy dx, that's 0. And dz dx, that's what we're looking for. This is what we want, right? Because we're interested in finding the partial derivative of z with respect to x, and the partial derivative of y, or partial derivative of z with respect to y. We want those two partial derivatives in order to construct tangent planes, linear approximations, and the like. So what we've got is an equation involving that derivative that I'm trying to find. So I'm just going to write it in another way. So I'll write it as, rather than the df dx, I'll write it as f sub x for the partial derivative. That's times 1 plus f sub z times dz dx. That's equal to 0. So now we can go ahead and solve for dz dx. And we get negative f sub x over f sub z. That's that first expression. Step 2 would be to differentiate with respect to y. And we would have a similar calculation to get dz dy is equal to negative f sub y over f sub z. So that's our technique of partial differentiation. So if this is a little bit confusing, what generally helps is just doing an example. So we're going to do an example next to see exactly what all of these symbols mean and the solution to the problem. So here's our example. Just bring it up in the bottom in case people are still copying. So we're imagining we've got a function of x and y. So sorry, z is a function of x and y, but they're all tied up together in this equation. So z cubed minus z plus 2xy minus y squared is equal to 0. So that's going to define a surface, but I'm thinking of z in this thing as a function of xy. So if I pick an xy value, then there's a z value that corresponds to it. And I'd like to figure out what a linear approximation is to this function at the particular point in question. Typically, in these situations, given a particular x and y value, there could be many different z values that correspond to that x and y. It's kind of think of like in calculus 1, we had a circle and we did implicit differentiation on the circle. If I just gave you the x value, well, there'd be a y value in the upper semicircle and a corresponding y value in the lower semicircle. One of them positive values, one of them negative values. And you'd have to figure out which one of those you wanted to use to construct the tangent line. Either do you want the tangent line to the upper half of the circle or the lower half. The same idea is here. So I'm just going to switch to the picture of what this looks like. So this is the graph of that surface. And that red point is the point we're interested in constructing the linear approximation or the tangent line at. But there are other values that have those corresponding xy values. In fact, there's 2 of them, 2 other ones. So I'll zoom in and I've drawn 2 other points on there. They have the same xy coordinates, just a different z coordinate. In fact, if I just draw the vertical line through the x equals 2, y equals 4 point on the plane down below, that vertical line intersects our surface in 3 points. That's not surprising, because if I look at the equation, it's a cubic in z. So if I fix the x value and the y value to be 2 and 4, then I have a cubic equation in z, so there should be 3 solutions, and in fact there are. So we can jot down those solutions just so that we can see. So if we plug in x equals 2, y equals 4, we get z cubed minus z plus 8 minus, let's see, is it plus 8, 2 times 4, oh, sorry, 16. 2 times x times y is 2 times 2 times 4 is 16 minus y squared, that's minus 16 is equal to 0. So z cubed minus z is equal to 0. So that means z is plus or minus 1 or 0. So there's our 3 different z values that correspond to that xy value. We're interested in the point where the z value is 1. So in terms of our diagram that I showed you, we're interested in the red point, not the other 2 yellow ones. And we'll see that diagram in a second. We'd like to find the linear approximation. So this is what we're interested in doing. We want to know what is L of xy. Well, L of xy, the linear approximation, is the z value of the point that we're at, plus the partial derivative of z with respect to x at the point that we're at, times x minus the x coordinate of the point that we're at, plus dz dy at the point we're at, times y minus the y coordinate of the point we're at. So that's our form of our linear approximation, which we've been using all along now for the last few lectures. So that means that we need to find dz dx and dz dy. And for that, we use the implicit, well, I won't even bother writing that out. I'll just say we're going to use the function f of x, y, z is equal to z cubed minus z plus 2xy minus y squared. So we're going to use that function. And our partial derivative of z with respect to x is negative the derivative, partial derivative of that function with respect to x over its partial with respect to z. So that's what our implicit differentiation technique told us above. So that means I just need to know what the partial of this is with respect to x. So that's going to be negative of partial with respect to x is 2y, all over the partial with respect to z is 3z squared minus 1. And in particular, we want to know at the point 2, 4, 1. And at 2, 4, 1, it becomes negative 8 over 2 or negative 4. We want to do the same thing. I'll put it in a different color just to indicate that it's a second calculation. We want to know the y partial. That's negative f sub y over fz. The y derivative is negative 2x. I'll put the negative around the brackets here. Minus 2y. And all of that is over 3z squared minus 1. And so if we plug that value 2, 4, 1 in for our point, we get the value of 2. And so now we've got our linear approximation. L of xy is equal to the z value of the point we're at plus negative 4 times x minus 2 plus 2 times y minus 4. And so there's our linear approximation. And we'll do the part 2 next day, but I just want to show you a picture for what we've just done. So what we have just done is we have constructed the tangent plane, or linear approximation is the function whose graph is the tangent plane. So we've constructed the function whose graph is the tangent plane to the surface at that point. So let's have a look at it. So I'm going to turn on exactly that surface we just constructed. It's 1 minus 4x plus 2y. If you work out exactly what it is, simplify it in this form. And that's what we did. We found the tangent plane to the surface at that point. So that's what we've done. We've just calculated the linear approximation. And the next part says to use our linear approximation. So to use this plane to estimate the value of z at 2.02 and 3.96. So if we move a little bit away from the point we constructed the tangent plane at, we're going to use the values on it to estimate the Z value on the point on the surface. All right, so I'm going to stop the recording here.